Hello. In a previous video, we looked at using the Po-Shen method to solve for the zeros of a quadratic expression or equation, and also to then use those zeros to generate the factored form of that equation. In this video, we're going to be looking at how to use the Po-Shen method to solve when the solutions are not integers. So in the previous examples, all of the zeros were integer values, +2, -2, 7, 7, 5, etc. For the example that I'm going to show you here, the solutions are not integer values. They're going to include radicals. And that's okay. This method is flexible and is able to be applied to any quadratic, which is what's great about it. Okay, so the first one we're going to look at is y equals x squared plus 2x minus 1. And if you were attempting to solve it using factoring, you would very quickly find that it's not possible to factor that and get a product of -1 and a sum of +2. It doesn't work. Okay, so using this Po-Shen method, we're going to find -b, so that's -2. We're going to divide that by 2, so that is -1. And the product value is coming from the constant term at the end here, which is also -1 in this case. It's just coincidental. So this -1 constant value represents the product of the two factors that would, if this was factorable. This -1, which is -b/2, represents the axis of symmetry, the location of the axis of symmetry, x equals -1, if you were to graph it. Okay, next step. So the zeros, which in this case are not going to be integer values, are going to be located at -1, this one here, and then some amount to the left, and -1 and that same amount to the right. So that's based on the fact that in any quadratic, there is an axis of symmetry, and the zeros or solutions are located the same distance to the left and to the right of that axis of symmetry. Okay, so now we're going to do the product of each of those zeros, like that. This is a difference of squares, binomials. It's going to generate 1 minus u squared on the left. When I isolate for u squared, I'm going to get +1, so that's 2. And when I square root to isolate for u, I get plus or minus √2. That's that radical piece that I was talking about earlier. So that means that the zeros are located at -1 plus or minus √2. And you could write them, one of them with the addition statement and the other with the subtraction statement, or you can state it more concisely this way using the +- symbol. And remember, it wasn't factorable, so there is no point in writing it in some kind of imagined factored form. So that's where you would stop, right there. So far, all of the previous examples that I've shown, and I'll have links to those at the end, the leading coefficient of that first term was 1. So I'd just like to show you an example with a radical result that has a leading coefficient that is not 1. That's a special case. So 3x squared minus 14x plus 1. If you tried to figure out a way to factor that one, you would very quickly find out that it isn't possible, it doesn't factor. Negative b is 14 divided by 2, that's 7. So I'm going to be doing 7 minus u and 7 plus u as my solutions. Next step is looking at where's the product. What is the product that we're looking for? That's this constant of plus 1. Now we're going to put 7 minus u times 7 plus u equal to that product. And I've just done the error that I was intending to demonstrate. The product is not 1. In this case, because of this leading coefficient of 3, that 3 is going to get multiplied into that constant term. So the product is not 1, it is 3. So I'm going to change that over here too. So that's the difference between how you would solve the problem if it had a coefficient of 1 versus not 1. Okay, so continuing on from here, that's going to generate a difference of squares. I have 49 minus u squared is 3. Isolate for u squared. That's 49 minus 3 is 46, which means u is plus or minus root 46, which cannot be simplified as a radical. I do take a second to look at it and see maybe it has a factor of 4 or something in it that I could take out of that radical sign, but in this case, I don't. That's 2 times 23, so there isn't any way to simplify that any further. So my zeros are going to be located at the value of 7 plus or minus root 46. And here's the second place where that 3 comes in. It's going to generate a division by 3. So one way of looking at this, considering what we're doing here, is in the initial phase of the equation, we multiplied by 3. So now we're dividing by 3 to undo that process. And the result here is a simplified rational expression that includes a radical that represents the two zeros that exist.